about the initiative, and then I'll introduce Melike. Okay, thank you. Welcome everybody to this webinar. It's sponsored by the IEEE Sustainable ICT Initiative. I'm Jafar Al-Mirghani. I'm one of the co-chairs of the initiative, and I co-chair this with my colleague Charles Dupin, who's not able to join us today. So I'll just say one or two words about the initiative, and then we will hopefully get started on the webinar. So initiatives are a way that IEEE tries to keep up to date and ahead in terms of technologies. And one of the key areas is sustainability. There are initiatives in different areas, for example, in smart cities, in big data, and so on. The IEEE Sustainable ICT Initiative has got a mission to build a holistic approach to sustainability through ICT by incorporating green metrics throughout the IEEE technical domains. So these initiatives cut across all different societies of IEEE, and the goal is to look at how we can use ICT to make other areas sustainable and how to make ICT self-sustainable, meaning reducing its carbon footprint. We have got a number of actions. We introduce standards, we introduce conferences and events, publications and education. And we try to break the silos between the different societies. If initiatives grow, they become a council, and if a council grows, then it becomes a society. So we're mainly sponsored by the IEEE Communication Society and with other societies. So, for example, the Microwave Theory and Techniques Society and Vehicular Technology Society, and so on. So far, we have delivered 9 IEEE standards. We have run 2 summits in 2017 and 2019, and we're running one next year. We have published a number of white papers, and we helped ComSoc introduce the IEEE transactions on green communications and networking with other colleagues and initiatives. We're working on an IEEE sustainability and ICT magazine, and we introduce a number of short courses. So if I can have the first slide, please. Okay, so it is my honor and pleasure to be able to introduce to you today a talk in the series of webinars that the IEEE Sustainable ICT Initiative has initiated. So those started early in this year, and we have had 4 or 5 of them already. Today's talk is going to be given by Melike, and is entitled "The Role of AI, Communication and Transactive Energy Systems in Sustainability." Our guest speaker is Professor Melike Erol-Kantarci. She's Canada Research Chair in AI-enabled next-generation wireless networks, an associate professor at the School of Electronic and Electrical Engineering at the University of Ottawa. She has made numerous contributions, a large number of publications, received a number of awards from IEEE and from the Communication Society, and it is a real pleasure to welcome you today. So whenever you're ready, Melike, over to you.
Thank you very much, Jafar, for this very nice introduction, and thank you very much for the invitation. I'm really happy to be giving this talk today. So let me start by sharing my...
And by the way, while that is happening, if you have any questions, please write them in the chat, and I'll be collecting those questions, and hopefully we'll have discussion towards the end. Thank you.
All right, I believe you can see my screen now.
Yes.
Okay, very well. Well, first of all, thank you everyone who sticked with WebEx, and I believe tried very hard to get into this seminar, because I was looking at the number of participants, and it's increasing slow by slow. Although we set the time to 9, I think there was a new download from WebEx, which you experienced, and you had to get over to get into the seminar. But I'm really happy that we have so many participants today. My name is Melike Erol-Kantarci. I'm a Canada Research Chair in AI-enabled next-generation wireless networks, and I'm an associate professor at the University of Ottawa. I'm also an IEEE ComSoc Distinguished Lecturer. So usually I give talks about either AI and 5G or AI and smart grids. And this time, actually, that was a great opportunity when IEEE Sustainable ICT Initiative reached out to me. Hey, do you want to give a talk on sustainability? I thought we're doing so many works on AI, communications, and smart grids. There is a really good amount of work that we can put into the framework of sustainability and show how these things come together. So the talk will progress in several partitions. First, well, it's almost following the same order of the title. First, some introduction of AI. Of course, it's not possible to cover everything, but only some tools that we use a lot in our research. And then how it is helping communications, and then how both of them are helping transactive energy systems, which are a relatively new concept in smart grid to help with sustainability. Now let's get started. And let me make my cursor a pointer, laser pointer, yes. So a lot of the times I get this question. And my chair is named like AI-enabled wireless networks. So people ask me, do you work on AI or machine learning? What is the difference? Aren't they the same? Or aren't you supposed to call your research something else? So let's get started with this basic definitions. So AI is the general umbrella for making machines more intelligent. And the goal is to make them as intelligent as human beings. Of course, this is very complicated, and it is not a task that has been accomplished. It includes inference, understanding, reasoning, controlling capabilities. But most of the time, we work with machine learning algorithms, which try to make some reason from the data available, or try to control the movements, the decision of an agent. And then there are deep learning architectures that help us tackle very difficult problems. So a part of machine learning, we can classify machine learning algorithms in generally four big categories. There is supervised learning, where you have a labeled data, and a machine, an algorithm, tries to classify new samples and determine whether they belong to a certain labeled set of data or not. Then there is another category of class of algorithms, which cover actually a large bunch of machine learning algorithms, unsupervised learning. Unsupervised learning approaches make sense of data without labels. And then there is another class, which is very dear to my heart, is reinforcement learning. Reinforcement learning is more to the interactive nature of learning and control of agents. This is something I'm going to talk a bit about in the rest of my talk, because we use it a lot in our research. And deep learning is, of course, provides us very compact architectures, representations, and it is useful in the other supervised, unsupervised, and reinforcement learning types of machine learning algorithms. Now, let's get started with reinforcement learning and explain how it helps to reach some intelligence. I'm not going to say human intelligence, because it would be too ambitious, but even reaching an animal's, cat's, dog's intelligence would be something fantastic. But what makes reinforcement learning or interactive learning interesting is that it is related to a type of learning that's into us, that's intuitive to us from our childhood. Because in the past research of AI, it was considered that if a machine was given all the rules around the world, it could become intelligent. But this is not the case for humans. So soon after, AI researchers realized that this is not the right way to go. Yes, you can have expert systems to teach a machine something, but you cannot maybe teach everything. There is the interactive aspect where, for example, we climb a tree, fall down, and then learn not to climb or climb more carefully. So some similar intelligence can be put into machines as well. And we call these machines agents. One of the fathers of reinforcement learning, as he formulated the MVPs, is Richard Bellman. So Richard Bellman applied this to optimal stochastic theory problems, and he formulated this problem, this control problem, using Markov decision processes. Now, we're going to talk about Markov decision processes, but I want to use some pictures, first of all, to better explain the concepts in reinforcement learning. So in reinforcement learning, we have an agent. Agent interacts with the environment. The state of the agent changes as a result of this interaction, and plus the agent receives a reward. This rewarding mechanism is very, very important. And remember your learning. Sometimes it's not a reward, it's a punishment or a penalty. Like you climb a tree, fall down, and your mother screams, and you freak out. So you learn not to do it next time, or you do something good and then you receive a reward. You could also make an analogy between Pavlov's psychological tries on animals, where you give a treat to a dog and teach some behavior. So these are very similar, but the difference, of course, with reinforcement learning and trial and error is that reinforcement learning happens in episodes. So we're not teaching just one action, we are trying to teach a sequence of actions to a machine. The sequence of actions are called policy. In reinforcement learning, we call them policy. And if you look at this figure on the right-hand side, you can see like there is branching out decisions, as we can see those lines, and then there is a bolded set of lines. So this bolded set of lines represents the optimal policy. These are all potential policies, but there is one that is optimal. Now, how do you know something is optimal, right? There has to be a numeric value to it. So that's something that we're going to talk very soon. Now, let's define the MDPs in a more formal way so that we can talk about the reward and then how reward is used. And again, I'm going to take it back and remind you, why are we talking about reinforcement learning? Because we use it a lot in comms and smart grid research. There could be many other machine learning algorithms applied, but our time is very limited, so I'm just going to focus on one type of learning, reinforcement learning, deep reinforcement learning, show a couple of examples how we use them, and then explain how they help with sustainability. Now, yes, getting back to Markov decision processes. So we have an agent. Agent has a state as at time t. That state is called st. And then it takes an action. That action is called as at. In state st, an agent takes action at, and the clock ticks. At the clock ticking, it receives a reward of rt plus 1, and it changes its state to st plus 1. Now, if we know the state, if we know the model of the environment, that's fine. We're going to know which next state will of our agent will end up. But for a stochastic environment, we need to have a probability. So that next state probability that we see over here, given that the agent is at state st, takes action at, it switches to the next state st with some probability. On top of that, we may have a system where reward is stochastic as well. So each time you are in one state and take one action, you receive a different reward. And imagine a gambling machine, right? You wouldn't get the same reward each time you do the same action. Otherwise, you would not know how to win. You would learn in time how to win. And then these sequence of actions happen in an episode. And that episode, you may make an analogy from a chess game. And actually, chess games, machines who play chess games, they use reinforcement learning. So that's a sequence of actions. And the policy is a mapping from states to actions. And then there is the optimal policy that you add up those rewards and you call the maximum value that gives out of these, that you can get out of these policies as your optimal policy. Now let's define it here. So as we said, policy is a mapping of states to actions. Each policy has a value. That means for each policy sequence of actions, we can add up the rewards as you see over here, get a numeric value and evaluate how good a policy is. Then when you have the maximum number out of a set of values, you say you can say this is my optimal policy. Now, we have a trick here. Of course, we don't simply add up the rewards. For a finite horizon MVP, we can add up the rewards without using this gamma discount factor. But for infinite horizon problems, which is most of the case, we have to use a discount factor gamma, which is between 0 and 1. What this discount factor does is it reduces the impact of the future rewards on the total value of the policy. And this makes a lot of sense, right? Because when you're playing chess, you are more concerned about what will be your immediate benefit from your next move rather than 10 moves, 20 moves later, right? I mean, because your opponent may change the whole strategy of the game. And yes, coming back to Bellman formulated this problem in a way that it can be solved with dynamic programming if we know the state transition probability. Now, here we start the optimal policy for the future states, the state transition probability, discount factor over here, and then the next reward is just over here. So we're trying to select the action that maximizes this whole equation. If we are working, as I said, in a model-based environment, which means we know exactly the model of the environment, we can use dynamic programming. But most of the times in comms and in smart grid type of problems, we don't know the model of the environment. There are a lot of stochastic things going on. So we're talking about model-free learning. And that's why probably in the papers that you have seen, read, or authored, you have used so much the term Q-learning. Q-learning is a model-free learning technique. It's one of the simplest ones. What Q-learning does is, and this was this concept was put forward by Chris Watkins in 1989 in one of his papers. Again, it makes a lot of sense because it helps you find the best Q values by looking at the differences of the future Q values and the current Q values. So basically, as in an optimization problem, you try to approach to a certain place, and if you're getting close, that's good. Then you're making good progress for either minimizing or maximizing your problem. But if you're getting far, then you have to try something else. Here, most of the things have been introduced. So this gamma is the discount factor that we saw before. Alpha is new to this slide. So alpha is the learning rate. What happens with the learning rate is it controls the step of learning. So if you go too fast, if you go with a big alpha, if you go too fast in learning, what happens is that you may skip some of the learning opportunities in between. If you keep it too small, then what will happen is you're going to have very small convergence. So all of these things are things to be considered. Now, the next thing is, anybody familiar with optimization problems knows that it is possible to get stuck in a local minima or maxima. So what happens in reinforcement learning is, this is also the case. This may be also the case. To prevent this, to avoid this, and to try new actions, we have a mechanism that's called epsilon greedy. Actually, that's one of the possible approaches, but most of the time we use epsilon greedy. The more fundamental or a better name for that is exploration and exploitation. So for exploration, our agents choose some actions that has some risk. So they don't always choose the action that's going to lead to the optimal policy. That may sound a little bit, surprising. Why don't we always follow, the sure path, the guaranteed path? Actually, it gives the agents to observe and see if there is a better reward somewhere else. So maybe you take some bad action for the moment, but 2-3 steps later, you're going to get a really great reward that's going to help you maximize your the value of your policy function, value of your policy. So that is called exploring. And when you are exploiting, you are using this information. A very well-known, widely used, almost de facto exploitation strategy is epsilon greedy. That's why I started with epsilon greedy. What happens with epsilon greedy is with probability epsilon, an agent chooses an action randomly, and with probability 1 minus epsilon, it chooses the sure action, the best action. and this epsilon is degraded to allow faster convergence. Now, so far so good. We have a technique to explore the environment, right? To take some risks. And then say, for example, if I go into this direction, I can get a better reward, or if I go into a different direction, maybe 5 steps later, I'm going to get a great reward. So our agent gets a sense of the environment, and always think of a chess game, like how it will play there. But the thing is, in some problems, because all of these value comparisons are done with respect to a Q table, that table may grow really large in time. So if we have too many states, or if we have too many actions, our state space grows exponentially. And this is called the curse of dimensionality. And another problem is Q-learning is suitable when we have discrete state and space. If state space is continuous, then state space and action space, actually, if they are continuous, then we have a problem. We can't use Q-learning. Then what can we do, right? We have a huge Q table. We have a big problem like we would have in wireless communications or smart grid research. Now, a nice way of handling this problem, addressing this problem, is to put a function approximator. And what does that mean? Now, imagine you're modeling some data. You have scattered data all around. What is the first thing you can do to reduce the dimension of the data? You just draw a line, a simple line to represent, to fit, right? To fit the lines. If your data is tricky, if it's too much scattered, then you fit a curve. So your parameter increases. If it's really, really tricky, then you go with polynomial size functions, and then you have to store all these parameters, but it's still better than storing the data. So that's the whole idea of it. So you start with regression, linear regression, and you go to more advanced filters. So aren't neural networks filters as well? Yes, they do filter data. They put some models to the data that you can represent with fewer parameters. So why don't we, instead of storing that big Q table, why don't we put some functions to model that table, and we just store the parameters of that function? So that's exactly what deep reinforcement learning is doing. It's putting a neural network in front of the reinforcement learning agent, and it's driving the reinforcement learning with those values. Now, let's make a very small, brief, open up a parentheses for those of you who are not familiar with neural networks. Just, let's talk about very, very basic concepts. So the roots of neural networks goes back to 50s, 60s, when Frank Rosenblatt started put forward the notion of perceptrons. Perceptrons can be considered as the ancestors of neurons in the neural networks. So how a perceptron works, or worked at that time, was we have inputs x1, x2, x3. They are making some, they're impacting the output with a certain weight. There is a decision circuit inside the perceptron, and the decision allows us to take a decision. Decision circuits allows us to make a decision about the value of the output. In this case, a simple threshold-based decision circuit has been used. The weighted sum of the inputs, if they are less than a certain threshold, the output will be decided to be 0. If the weighted sum of the inputs is greater than a threshold, then the output will be decided as 1. This is very simple, as you can see, but this is a general notion of neural networks. So this is one perceptron. If we put neurons, if we make them, if we use more sophisticated decision functions like sigmoids, arctangents, instead of this basic threshold function. And then if we organize the neurons in layers and in multiple layers, we get the neural networks. Actually, when we have them in multiple networks, we're going to call them deep neural networks. So if we have one input layer, one output layer, that's a shallow neural network. If we have any hidden layers, plus one hidden layer, makes a neural network a deep neural network. Deep architectures are good because they can help us with representations. Actually, in theory, with a straight line of neurons with a single layer, we should be able to model any function. However, we have to use a lot of neurons to be able to do that. So we organize them into layers so that we use less neurons to model the problem. So there are many different types of neural networks. Some of you might be familiar from different fields, like CNNs are very popular in computer vision. And RNNs are have been very popular in NLP, natural language processing. Actually, the funny story is, this is related with the history of AI. Around 60s, 70s, there was a funding cut in AI because the NLP research at that time, they weren't using the RNNs. RNNs were not there, basically. Was not very successful. So during the Cold World War, the text from Russia was coming and the machine's output was just not making any sense. So basically human translators were still needed to be used. So all that funding seemed a little bit for nothing. So there was a cut down on the funding. However, some people kept on working on these concepts, luckily, and then they came up with something called RNN. After RNN, the beginning of the 2000s, there was a great success in NLP. And this success is actually based on the structure of RNN. If you look at an RNN, it can store the temporal behavior in a data. And when you think of language, we keep repeating the same things. So if a machine, an algorithm, can remember what has happened maybe a million steps behind, that would be successful in NLP. Now, for us, of course, we are not working on NLP. How are we going to use RNNs? We are going to use a special type of RNN, which is, again, a very popular tool in deep reinforcement learning that is called LSTM, long short-term memory. The beauty of LSTM comes from the fact that a unit has two inputs. So number one is a memory unit, which we didn't have in other neural networks, which helps us to remember previous steps. And of course, remember has a counterpart, forget. So you have to know how much of the previous information you need to forget, because if you remember always everything, that's not good for you, and that's not good for an algorithm as well. So we have a forget gate for that. But anyhow, I'm going to come to that. So we have the output from the previous LSTM unit, as it should be in any neural network. Yes, here's the forget gate. So we put this memory function, this memory input to the output of the same unit, and we apply certain functions to basically leave some information behind and retain some of the information for future layers of the RNN. And we have the output gate as it should be, and we have two outputs, the memory from the current unit, and the output from the current unit is passed over to the next unit of the RNN or LSTM. Now, the beauty of LSTM, as I said, comes from the fact that it is very suitable for using in reinforcement learning, deep reinforcement learning problems. And at the beginning, I said, like, oh, if we put a neural network in front of reinforcement learning, that's going to work. Well, that's a bit naive, okay? So we have to also do some tricks to make it work. And I'm going to explain why it is naive and what's wrong with that approach. But first of all, most of the studies that are using deep reinforcement learning are inspired by an article in 2015. So it's not too far away. It was published by Google DeepMind researchers in Nature, and they described an architecture of deep reinforcement learning that has some special properties. For example, a deep neural network and a target deep neural network, where we keep copying values from the actual deep neural network and keep sort of a memory of what we have done. And then an experience replay memory to keep a mini batch of the samples, good samples, to drive reinforcement learning actions. Now, you will see that I have some concepts of wireless here because we used it a lot in my research for 5G and 6G. So we have a G node B over here, so that's inside the base station. But I mean, it's not limited to just base stations. For any agent, any smart algorithm, you can apply this. But just for wireless, what's happening here is that we have the wireless environment giving a feedback, like for example, CQI, that is driving the DRL algorithm, and an action is taken by the base station. Action could be, for example, resource block allocation. So yes, I was just saying, we have this nice thing, and previous what I said is naive. And the reason is because we have stability problems if we just put a neural network in front of an RNN. In 2015, in this article, the authors show that if we copy values to a target deep neural network, it becomes easier to tackle the stability problem. Now, let's get started with a little bit, how we apply this. So this was mostly on the theory side. We talked about reinforcement learning, deep reinforcement learning, but how on earth are we applying it to research, to apply to problems? One great area where a lot of the researchers and myself is applying AI or these type of machine learning, I called it AI, but actually I'm referring to RL and DRL algorithms, is actually many things in 5G and 6G communications. And the reason why we are doing this is because these networks are becoming much more complex than LTE. In LTE, we had self-organized networks, which gave us a little bit of capabilities of configuring the base stations at the first initial deployment and some small optimization tasks. But in today's networks, we have heterogeneous devices with heterogeneous service requests. We have small cells due to millimeter wave, so there has to be smart algorithms doing beam tracking, resource allocation. We have the flexible numerologies in 5G. And then, as I said, we have mobile users, heterogeneous users, and then we may want to, most of the time, make the best out of the spectrum use, so we may like to jump into unlicensed spectrum. So all of these things are making the network very complex and requiring AI algorithms. I'm not going to talk about, the schemes that we propose today for 5G or 6G. But if you are interested, in 2019, we had an article in Vehicular Technology magazine, and over there we summarized some of the challenges, opportunities, and so some examples how we applied it in comms. Now, comms and smart grid goes hand in hand because comms, communication technologies provide the underlying infrastructure. Of course, wireless is not the only thing, the only facilitator of communications in smart grid, which helps us with sustainability. There are other communication technologies, but just as an example, like AI helping comms, comms helping smart grid, and then having machine learning algorithms also to control smart grid functions is actually a great opportunity. And all of these things, like for example, being able to forecast the load or generation of renewable energy, are directly related with sustainability, because if you want to make efficient systems, first you have to have a foresight of the system that you are working with, and then you have to have access to control. Control can have many directions in smart grid in the electricity system. Residential energy management is one of them. We can control how much energy is consumed by a home. We can control the peak hours and make the grid efficient, because as you know, renewable energy generation is intermittent, so it's not always available. And we see that there are many countries, actually very recently, President Biden announced that US will be increasing their reliance on solar energy. So that means that we're going to have intermittency in the grid much more than before. And we have to have smart algorithms to manage our loads so that we don't have any interruption of service. So the works that we do around residential energy management or electric vehicle charging, discharging, usually falls under the efforts of using renewable energy in a way that it won't really cause any problems and outages. And then microgrid control. So microgrids is a different concept that is classified under smart grid, but research had started on microgrids much before then the smart grid word was first pronounced by actually President Obama in 2007. And so microgrids were studied by Navy in case you go to a hostile environment, you have to have your own grids without any reliance to the outside grid. But today we don't use microgrids for that purpose. We are using or trying to have microgrids so that they can trade energy between each other. So they can generate, use it with their own purpose, and then sell the surplus to their neighboring microgrids. And if you know Brooklyn microgrid, that's a great example of this, where the users inside the microgrid trade energy. That's something we call as transactive energy. So as you can see, all of these things are really closely tied together. So I'm not going to talk about, the works that we did in each and every area because we are limited with time, but I'm going to use the next 5 minutes to talk about some of our recent research in this area. So some of the research that we have done was, more than 10 years ago when these things were just first being pronounced, and then some of the things that we did in this area are quite recent. I'm going to focus on a bit on energy trading here, or transactive energy systems. So imagine we have microgrids, and within a microgrid, inside a microgrid, owners of solar generation or solar generators, storage, and demand may be different. And consider another case where we think about a microgrid as a black box, couple of microgrids together, and they can sell or buy energy from each other. Of course, we will always have utility grid as a backup, but the purpose of this is not like to diminish the utility grids all at once, or at any point, because we need the distribution lines. First of all, we need the control, but if there is some surplus generation, why don't we use it in a in a good way? This can be also sold to the utility grid, or this can be shared among the microgrids, either by selling or just by sharing. And I'm going to show one example where sharing actually makes sense. So these studies around AI using machine learning for energy trading has started very recently. We have some works in the area, and there are other research groups all around the world, working on such problems. And it comes back to reinforcement learning again, where we have an agent trying to decide what's the best policy to sell or buy energy from another microgrid. I'm going to introduce more specifically, gonna get into the depths of this in one of our papers where we used correlated deep Q learning. It's a little bit different than deep Q learning. We used it for microgrid energy management, where inside the microgrids, PV is owned by one entity, energy storage system is owned by another entity, and DSM, the load, is belonging to another entity. And the purpose here is that the PV may sell electricity to the main grid or the load. ESS may charge from the PV or sell to the load, or it can also interact with the utility grid. So as you can see, this is a fairly complex system, even though we have 3 agents that are trying to decide what is the best strategy for selling or buying electricity. We have, so the deep part of this comes from the fact that we are using LSTM to drive our reinforcement learning. And the storage system, PV and DSM, is modeled as agents. So they are the agents of reinforcement learning. They use their memory to decide to take the best action. But the thing is that they're also using the correlated notion, correlated game theory notion, or correlated equilibrium from the game theory, to reach an agreement, because in such a system, we can't really rely on agents taking independent actions. So my cat is interfering with my WebEx. All right. She has found a nice spot behind my laptop. That's good. So Yes, let's continue with correlated equilibrium. So correlated equilibrium is more general than Nash equilibrium, but in theory, it is very close. So what will happen is that the agents will reach a strategy, which is a set of actions. That's different than Nash equilibrium. They will reach a set of actions, and that set of actions will be the case where, you know, none of the agents, if they change their policy, will not be satisfied. So just like in Nash equilibrium, they find the best policy or best set of actions that will lead them to an optimal situation. Now, when we look at the results of this correlated equilibrium, and I know that I'm running out of my time, so I'm not going to spend a lot of time, but we can just show here that by deferring appliances, we are able to shift some of the load, first of all, to different hours, then make use of the solar energy when it is available. So that's very important for sustainability. And then overnight, use other resources, especially the batteries that we have charged during the daytime. So we compared correlated deep Q learning with an independent deep Q learning technique and showed that the profits of a customer would be much more than that. So in the next part of my talk, I actually have a scheme that I want to talk about too, but it looks like the time would not allow for me because I want to leave some time for questions as well. So all I want to show here is that we can combine the three things together: AI, machine learning, and AI, comms, and smart grids. And this was something actually we started in 2014 when I was an assistant professor at Clarkson University in Potsdam. That's a small town in the US where the winters are brutal. So power lines may freeze and you know, suddenly a system may be cut down from the one of the microgrids may be cut down from the utility lines. So, and this is one of the examples that I can say that energy sharing makes sense, because we were thinking like the hospital that didn't have any generation capacity could benefit from the electricity produced by the solar panels at the universities. There are 4 universities in a small town, and they all have large fields, so they have some solar panels. Why wouldn't they supply the little village and especially the critical services? So that's what we tried to do there, but then we needed a very low latency communication, so machine learning came into the picture with that. And later on, actually more recently, we had research on how to use device-to-device communications and side link channels. And this work is interesting is because for a lot of the times when I was doing, at least for my research, there was a big desire to have a simulator, co-simulator for smart grid and LTE. With this work, we actually did it, and its code is on GitHub. So anybody who's interested can reach that. And that simulator can create some events in the power grid. I mean, the simulated power grid, for example, excessive load, transformer overloading, and then comms algorithms can be developed. Like, for example, in our paper, we developed a reliable Q learning approach, which we showed it was better than the standard LTE mechanism with having less disturbances. So I'm going to finish my talk by thanking my students, because you know, all this great research is only possible with the hard work and dedication of students, as well as the generous support of funding agencies. So we are supported by the NSERC of Canada, NSF of US, MITAX of Canada, Ontario Centers of Excellence with the Encore 5G program, and the Natural Resources of Canada. So I'd like to thank you very much for attending the seminar, and I'd be very happy to answer your questions.
Thank you. Thank you so much, Melike, for this very fascinating talk and so many areas that you have touched upon. So we have a number of questions. So the first one of these questions talks about using neural networks in or in reinforcement learning. So the question is, what is the criteria that should be used in order to choose or design a suitable neural network for function approximation in an environment with continuous state and action space? So you talked about when the action space and state space become very large, you can start using a function approximator. So the question is how to choose a suitable neural network given a given setting for a given problem.
That's a very good question. And we sometimes deal with continuous state and action spaces. And in those cases, we use policy gradient methods. For example, actor-critic learning is a very well-known such a technique where we don't work on discrete spaces.
Okay, excellent. And so another question is deep learning suitable for real-time applications?
Well, deep learning and maybe reinforcement learning, we can talk about them both. It is true that reinforcement learning has a large convergence time. As a matter of fact, deep learning helps us to tackle larger size problems and reduces the convergence time of reinforcement learning for such big problems, let's say. But still, especially real-time applications, that would be very challenging. For those, we have some schemes that we use transfer reinforcement learning. So these are fairly new. Our papers are just published in Transactions on Wireless Communications. I can share the information if the audience is interested. And these are for reducing the convergence. However, no matter how much we reduce, yes, there is a training time for machine learning algorithms, and for real-time applications, you have to have a strategy. One strategy is offline learning, but then you have to have a very stable system. If you have any non-stationarity in your system and you have to relearn things, then you have to think about the cost of learning and the convergence.
Excellent, thank you. So there is a question here that talks about the interplay between optimization and energy efficiency. So it starts by thanking you for this fascinating talk. And it asks, do any of your algorithms specifically break out optimization for data throughput versus energy efficiency?
Yes, that's a very good question. Actually, I didn't cover our works on energy efficiency and where we look at the trade-off between, regular KPIs like throughput, latency versus energy efficiency. But we have works on this, especially very recent works on carrier aggregation in 5G. So they are not in the line of smart grid research, but for 5G, as some of you might know who are interested in this area, carrier aggregation that has been proposed for LTE is still a technique that we use. And it is something very, very challenging, actually. It sounds very simple, like you collect a bunch of spectrum together and call them like aggregated carriers. But at the same time, so with that, you can get a lot of throughput, but at the same time, for the users, they have to monitor all the active CCs, so they have to spend a lot of energy. So we have works, some works using machine learning to address the trade-off between throughput latency versus energy efficiency from the user perspective.
Excellent, thank you. And I think you got people really interested and fired about this area, so many more questions coming. So one of the questions asks about the energy consumption of the machine learning algorithms themselves. I guess you touched upon this a bit, but I don't know if you wanted to say more.
Yeah, that is a very good question. I mean, most of the times we assume that these machine learning algorithms are being run on equipment like base stations where there's not a really big concern of energy consumption. Like you're not running on an IoT device and you're going to run out of their battery because you're using a machine learning model. But it is true that these machine learning algorithms do consume energy. And then if you were to run it on an IoT type of device, then it would be a big problem. Currently, we are not really studying how much energy cost we are incurring with these machine learning algorithms, but I know in the literature there are works, especially in the area of IoT, how to come up with energy efficient ML algorithms for resource constraint devices. So if the if the person who's asking the question is interested, they can send me an email and I can share some research works in this area.
Excellent. And I guess we are planning to share your slides afterwards, isn't it?
Mm-hmm.
Yeah, okay. And there have been questions about these. So maybe we can take a couple more questions. So one question asks about how can energy management in microgrid be carried out using AI?
Mm-hmm. Oh, I see. So in microgrids and in home energy management systems, actually we have devices, so controllers that are sitting in some locations, and these controllers are basically can be considered as very small size PCs. So they have their processors, they have their memory. And the assumption is that our machine learning algorithms are running on such machines. I'm not sure if I understood the question clearly, but if this doesn't answer, they can ask it again.
Okay, no, I think you addressed the point. It was more on how you're using the algorithms, I guess, in the microgrid area. There is another question about the possible areas of research in sustainable computing. I guess this is just a bit broader, but if you wanted to give maybe a bit more insight, that would be useful.
Yes, this is very good because that's something I did not touch upon. So I really like questions, when they come and it's on something else that we probably missed to cover, and that gives an opportunity to talk a bit about them. Well, frankly, as you said, it's a big research area. I didn't even, cover a lot of the research that is using renewable energy at data centers and in a smart way that is scheduling loads on different parts of the world. And I can say that actually the host of this meeting, Jafar Kani, has a lot of work in this area. So again, I can share some of his papers and other colleagues' papers in this area. So sustainability and sustainability in computing is something that is very, very active, and applying machine learning has become, again, another very hot topic in the recent days.
Excellent.
Just like many of the research areas nowadays, it's very popular to apply AI to many things. And the main reason is actually, I get asked this a lot. The main reason is not because we find it very fancy that, we're trying something just to try something, but our systems are very, very complex. You look at comms, you look at computing, you look at smart grids or transportation, a lot of things. They're becoming much more complex than before. Plus, we are having much more data than before. So these data-driven approaches and intelligence of AI is something needed a lot in our research these days.
Thank you. And just, I guess, a very final question. So it asks, how does reinforcement learning help IoT to train machine learning algorithms locally instead of processing them remotely in the cloud? Our aim is to avoid activating large data centers for training these algorithms to save energy consumption. So I guess it is more along the lines of how can we do local processing and make use of IoT devices.
Very good. Again, another question that helps me talk about something that I did not cover in the talk, which is federated learning. I'm sure many of you have heard about it. This is relatively recent, developed after Google people find out a way of training individual smartphones, their keyboards, like the usage of keyboards, without storing all the data in their own servers, just by using the local data. So that gives us an example. I mean, phones can be considered as an IoT device, but most of the times we are thinking about more resource constrained devices. But still, federated learning techniques can be used to benefit from the data that's on the device, both avoiding activation of large data centers, also avoiding sharing the data with the data center. So sometimes you don't even want to send your data for training. You want to do the training locally for privacy. And then you get a win-win solution. You don't activate the servers far away, you don't incur the latency, and then plus you get the privacy.
Excellent. Thank you so much. I guess with that, maybe we can conclude the seminar, webinar. I know there are more questions and we did not manage to get through everything. So Melike, if you are happy with that, maybe we can collate the questions and maybe write some answers and share them with the people who've asked the questions. Is that okay?
Absolutely, that would be great.
Yeah. Excellent, thank you. So in the end, I would just like to thank everybody so much for joining us, for being here, for asking all these questions. And I hope you found today's webinar stimulating as I did, very interesting, very deep, very knowledgeable, Melike. So thank you so much for sharing your knowledge with us and the time as well. Hopefully we're going to continue with this series of webinars, and next month, and I guess just once a month, we will continue to have those. So please keep an eye out for the invitations coming out. In the end, thank you so much, Melike, and hopefully we'll hear more and interact more with you. Thank you.
Thank you very much, Jafar, for hosting the webinar. Karen, you too. Thanks for the all the efforts you made for publicity, for arranging this meeting. That was a pleasure, and thanks everyone for attending. And as Jafar said, I'd be very happy to answer questions. So if you have any questions, please do send them to us, and I'll try to answer them to the best of my capability. Thank you.
Great.
Thank
and
you.
from IEEE, thank you all. Thank you, Melike. Thank you, Jafar. And thank you for all the attendees. We really appreciate your support of IEEE.
Thank you. Thanks, Karen,
Thank
for
you.
putting all of this together. Thank you.
Absolutely.
All the best. Thank you.
Take care.
Have a nice day, everyone. Bye-bye.
Thank
you.
Bye-bye.